Welcome to a brand new installment of Singh Sciences, where today we'll be discussing radioactivity and the photoelectric effect. So, radioactivity, also known as nuclear decay, is the process of particles or electromagnetic radiation being emitted from an unstable atomic nucleus. Backtracking for a bit, we all know that the nucleus is composed of protons and neutrons tightly packed together. All these positive protons are held together in such a tight space, even though we know from basic physics, like charges repel. The only thing holding these protons together is a strong nuclear force induced by the gluons inside the neutrons. However, sometimes these internal forces within the nucleus can be unbalanced due to an excess of neutrons or protons, resulting in an unstable nucleus. In fact, any nucleus with more than 82 protons is considered unstable. Looking at this decay chart, we see the neutron to proton ratio required to balance these forces and stabilize the nucleus. When the nucleus strays from these ratios, decay occurs in the form of alpha, beta, or gamma decay. Alpha decay is a process in which an atom's nucleus sheds two protons and two neutrons, which is a helium nucleus or alpha particle. For example, uranium 238 will decay to form thorium 234 by ejecting an alpha particle, and the resulting nuclear equation would be this. Another form of radioactivity is beta decay, which consists of either beta plus or beta minus. Beta minus decay is the process in which a neutron ejects its associated electron and becomes a proton. If cesium 137 undergoes beta minus decay, it will produce an electron, antineutrino, and barium 137. Accordingly, beta plus decay occurs when a proton transfers into a neutron and ejects a neutrino and a positron, which is the same mass as an electron, however, it holds a positive charge. Sodium would undergo beta plus decay as shown in the following nuclear equation. The final form of radioactivity is gamma decay. Gamma decay occurs due to an excess of strong nuclear force. This excess energy is released by the ejection of gamma waves. The number of protons and neutrons, however, do not change. Radiation is usually measured in the SI unit becquerel by a Geiger counter. 1 BQ is equivalent to an inverse a second and refers to the amount of nuclear disintegrations per second. Meanwhile, the energy of a radioactive particle is measured in electron volts, which is equivalent to 1.6 times 10 to the negative 19 joules. Ernest Rutherford is credited to have classified the three primary types of radioactivity by determining how they penetrate matter. Rutherford discovered that alpha radiation could only travel a few centimeters in air, beta radiation could travel several meters of air or a millimeter of aluminum, and gamma radiation can penetrate a meter of concrete and several centimeters of lead. Due to an alpha particle's relatively large mass compared to an electron or positron, double the electric charge, and a much lower speed, it tends to interact more with the surrounding environment and as a result come to a stop quicker than beta particles. Meanwhile, gamma rays are the most powerful as they have absolutely no charge and electromagnetic fields are not able to alter its path, thus allowing gamma rays to travel very far through most types of matter. Radiation is crucial in society and science due to its applicability. For example, many cancer treatments involve radiation where a radioactive substance targets a malignant growth and ionizes or breaks apart bonds in the DNA of the cells, preventing replication of the disease. Apart from medicine, radiocarbon dating is used to trace back events of up to 50,000 years. Carbon 14 is a radioisotope of carbon that an organism takes in while it's alive. However, after this organism dies, no more 14C is introduced. The half-life of this isotope allows scientists to see the past. Radiation's applications in science are also endless, with the most noteworthy appearance in the Hershey-Chase experiment. In order to determine what the genetic information of an organism is, Chase and Hershey labeled the proteins of a bacteriophage with radioactive sulfur and the DNA with radioactive phosphorus. After letting the bacteriophages infect the host cell with genetic information to reproduce, Hershey and Chase discovered the presence of radioactive phosphorus in the host cell, allowing them to conclude that DNA holds genetic information. Moving forward, the photoelectric effect is a low-energy phenomenon when a photon, a quantum of electromagnetic radiation or light, strikes an electron on a metal surface and the electron is ejected. The electron can then be described as a photoelectron. Before Einstein's revolutionary thinking, it was believed that light acted solely as a wave. This classical electromagnetic theory stated that the photoelectric effect can be attributed to the transfer of energy from the light waves to an electron. This theory would infer that a change in the intensity of the light would induce changes in the kinetic energy of the photoelectrons, so a higher intensity would result in a higher kinetic energy. On top of this, an extremely dim light would show a lag time in between an electron being removed from the metal and the initial shining of the light, as it would take longer for sufficient energy to transfer to the electron. It was also believed that the frequency of the light did not impact the kinetic energy of the electron, only the intensity of the light did. All of these assumptions were proved to be incorrect through experimentation. So Einstein proposed that a beam of light is not a wave, but rather a collection of discrete wave packets called photons. Einstein believed that a photon would collide with an electron and transfer its energy, allowing the electron to escape and destroying the photon in the process. The photon must transfer a minimum amount of energy in order for the electron to be ejected from the attractive force of the metal. This is called the work function. If the photon has less energy than W naught, then the electron will not be released. However, if it has more energy than the work function, The remaining energy, as stated by the law of conservation of energy, is converted into kinetic energy for the electron. As a result, the kinetic energy plus the work function equals the energy of the photon. However, the energy of the photon can also equal Planck's constant times F naught, where F naught, the fundamental frequency, describes the minimum frequency of light required to rip an electron off of a certain metal, similar to the work function in a sense, while Planck's constant denotes the energy of one quantum of light to the frequency of that radiation. This equation directly contradicts the classical theory as the frequency directly correlates to the sum of the kinetic energy and the work function. The intensity of the light does not impact the kinetic energy of the electron, however, it does dictate how many electrons will come off. A higher intensity results in more electrons being removed from the surface. Through experimentation, it was shown that there is a cutoff frequency for when electrons stop being ejected from a surface, and that a higher frequency results in a higher maximum kinetic energy for the photoelectron. As a result, there is clear proof that light does travel in packets called photons and acts as both a wave and a particle. So the photoelectric effect is vital for solar energy and occurs in solar cells. Light strikes the cathode of the panel and causes the emission of electrons. The work function of the cathode is low in order to maximize the energy output of the electrons. The electrons produce a current after leaving the cell, and usable energy is generated for human use. This phenomenon is also used in garage doors, where a photoelectric device called a photocell creates an electrical current when light strikes it. When the light beam is interrupted, electron flow stops and the garage door opens. The photoelectric effect also earned Einstein a Nobel Peace Prize for discovering the wave-particle duality of light. It was this very concept that allowed for future scientists to expand upon quantum mechanics, such as allowing Werner Heisenberg to develop his uncertainty principle. Thank you for joining us today on Singh Sciences, and stay tuned for our next episode.